Okay, good morning. I continue to the next chapter. The next chapter is actually a very good chapter. It includes a lot of nice mathematical concepts, but it starts with section 5.1, which is problem solving strategies. So in principle, you have learned a lot of mathematics during your high school education, so you should be able to somehow use them to solve some problems, yes, without... So you need to understand what type of mathematics you really know in order to be able to solve the problem. So it's very important, by the way. Sometimes you know mathematics logic for solving a problem, but it's not easy to realize that you have all the machinery that you need for solving the problem. So that's very important. So somehow you need to learn how to evaluate your knowledge of mathematics. Is your math knowledge enough to solve a problem or not? Yes. So what I see in the book, they are written as, okay, if you want to solve a problem, first of all, you need to understand the problem, and then you should have a plan, which I was always talking about. You should have a strategy, yes? You should have a strategy, otherwise randomly doing things is not very helpful. And then at the end, you have to find a way, which is technical part, how to implement your plan or strategy to the problem. And then, according to the book, you have to go back and see if the answers that you get are reasonably correct. Yes. For example, if you're supposed to find the weight of the, I don't know, raindrop, if you get it 1 ton, probably you have made some mistake somewhere. Yes. So it should be reasonable. And then one thing that I want to add here is that if you want to be a good problem solver, you have to get experience and remember somehow this experience, which they haven't mentioned. That's extremely important. Otherwise, you have to start every problem from scratch from the beginning. Yes. So that I would recommend you if you want to be a good problem solver. It's really important to take lessons from the problems that you solve and somehow keep some salient part of that in one part of your memory, so that if you want to solve another problem, might be that will help you to solve that problem as well. Okay, so there is no lesson for section 5.1. They have actually arranged a lot of problems, a list of problems here. We want to try to solve them, but from the next section, there are very interesting mathematical information again coming in. And I will try to cover as many parts as we can, okay? So, the first thing, let me start with problem 5003 in the book. Yes. So the problem is this. Determine the point on the parabola y equals to x squared. So a point P is missing. You want to find this point P on the parabola, probably the simplest parabola ever, y equals to x squared, which is the closest point to the point Q with coordinates 4 and 0. Yes? And then you want to also determine the length of line segment PQ. So in principle, you want to find the shortest distance. So is the problem clear? So that's up to you, by the way. This is the strategy of solving problems. So if I want to solve the problem, first of all, I read the problem 1 or 2, probably as many as time I need to understand that. So the point is that I have a parabola, and I want to find a point on the parabola whose distance to this fixed point is minimum. And then, of course, I want to find that minimum value. Okay, so this is one, I read it. And then if I want to have a plan, I usually sketch, if possible, I try to draw some or sketch some graphics to visualize this. So, and you shouldn't be obsessed with precisions and things like that, of course. If you have a computer available, you can do it, but don't rely on those computers that much, because these problems are not hard. So I have this parabola. Everyone should know at this level that this at least looks like this. And then point 4 and 0 is a point on the x-axis whose x-coordinate is 4. So this is my point Q. And then I want to find a point somewhere here, which I will call it P, so that its distance to this point is minimum possible value, yes? So what I do, of course, I hope that you agree with me, eventually we will not find P on this part, yes? This is my prediction. Because it seems intuitively that the points on this branch are farther than the points on this branch to the point Q, yes? So, I mean, you don't need to be worried about that part yet, so I want to find P so that this distance becomes minimum. So this, what I have done here, is actually the part that we, the first part, reading the problem, understanding, and then this is somehow part of my understanding about the problem. Yes, that's the first step that I do. Then I should have a plan or a strategy to do this. Okay, so I want to hear from you. I think it would be better if you cooperate with me in this kind of problems. So first of all, you should have a good assessment about your math knowledge. Do you think this math problem is at the right level that you know? So somehow you need to remember what part of mathematics that you have studied so far is somehow related to this. So let us understand these things, by the way. So can you tell me what things you predict will be useful for this problem? What parts of mathematics that you have learned from Math 1C up to Math 4 and Math 5, some of you even Math Specialization. So which parts of mathematics is related to this problem? You should have a rough idea of that, otherwise it would be hard. Can you, yes?
The formula for calculating the diagonal from point P to Q.
Which is called the distance formula, if you mean.
Yes.
Yes?
Formula.
The distance formula. Definitely it is relevant. Why is that relevant? It's not hard to see, because I want to talk about the distance of 2 points at the end. So the distance formula from Math 2C is relevant. What other parts of mathematics might be relevant? Because this is the way that I think, I don't know, I do it somehow unconsciously, but this is probably the way that I do. So when I see the problem, the formula, distance formula comes to my mind immediately, because I want to find the distance between these. But what part of mathematics is also needed? Yes, please?
Minimizing a function.
Yeah, minimizing a function, because I'm interested somehow in the shortest distance. Shortest distance means minimizing a quantity. Okay, and then if I understand this, for minimizing the quantity, what I should have? Of course, there are some exceptions that we can do it without the notion of derivative, but if I want to do it generically, I need to think about derivatives, yes? Because that's I hope that you learn this very good, that minimizing somehow is related to the notion of the derivative. But for the derivative, this is the way that you need to think. For the derivative, you need a function. And somehow the target function is the distance formula. So what you do, you start doing that, you start actually trying to find the distance as a function of some quantity, a parameter that probably will decide which parameter. Okay, so what do you think? The first thing comes to my mind is that, okay, P is on this parabola. Do I know P? No. So X coordinate and Y coordinate are both unknown. But in principle, I have one single unknown, not two, yes? So I can call one of them X. The other one, I can call it Y. Don't do that, because you are bringing two variables into one problem. If possible, try to keep the number of variables in your problem as low as possible. So what do you suggest me for writing instead of Y? X squared, yes, because this point lies on this parabola, so if the X coordinate is X, the Y coordinate should follow. This becomes X squared, yes? And then I want to find this distance. So this is the distance that I call it D. And I want to find the distance. We know the distance. So the distance is equal to the square root. So this is the way. If you have forgotten the formula for the distance, you know. So because you might have a handbook of mathematics including thousands of formulas, you really need to know where to look for, yes? So this means that at least you know what to do. You go find a formula, but I prefer to have it in my memory. These are very famous ones. So then I would write the difference between the X coordinates squared and the difference between y coordinates squared. This is the distance between these two. And then this distance is depending on x, and x is changing because p is free now to move on this parabola. So this is a function, but a function of which quantity? Of quantity x, which is the x coordinate of the point p. So that's my function. Yes? So what I do, I would say that dx is equal to, let me simplify as much as possible, x squared minus this 1 to power 2 is x to the power of 4. This one is x squared, and then 2 times the first one times the second one, and then finally the second one squared. So that is the function that I want to minimize it. Yes? Any questions so far? Okay, so the next step would be taking the derivative. Yes? So when I take the derivative with respect to x, so d prime of x, then there are some technicalities come into the game which you couldn't anticipate. Yes? So you couldn't anticipate. So which rule of derivative becomes important? Suddenly the chain rule becomes important. Yes? Which you couldn't see prior to the starting the problem. Yes? So the chain rule, actually you know. So you need to know about these, otherwise, so you, of course, you know where to look for it. I want to calculate the square root of u, where u is a function of x itself, and then differentiate it. So it becomes 1 over 2 square root of u, but multiplied by u prime. Yes, so what I do is that 1 over 2 square root of x to the 4 plus x to the 2 minus 8x plus 16. And then you multiply it by the derivative of this one, which is so simple, don't waste the time. So it becomes this, yes? Okay? So this is the derivative. And then what should I do? Because you know that if you want to minimize, you have to put this equal to 0 and find the candidates for minimizer and maximizer. But of course you have to be careful as well about the, might be one of them is a minimizer or maximizer or even a terrace point. So you have to be careful about that one as well. Okay, so then what happens here is that I put d prime of x equals to 0. So then this means that this fraction should be 0. And then what happens here is that if a fraction is supposed to be 0, its numerator should be equal to 0. Yes? So this means that this implies that 4x to the power of 3 plus 2x minus 8 is equal to 0. And then what I have to do, for example, I want always, these are technical things, you know, so you need to be able to solve a lot of problems to do these things fast, but of course, immediately you should be worried a little bit. Why? I'm also worried, because whenever you see a third-degree polynomial, you should become nervous, yes? Because you don't know how to solve it. There is no formula, so we have to think about it, okay? So I divide by 2, okay, so to the power of 3x and the... So by the way, I haven't solved this problem before, so that's good to see how it goes, okay? So first of all, when I come to this point, because that's not very common to solve the third-degree polynomials, I start checking my calculations once more right here, yes? To see if I have done any mistakes. Okay, so do you think, did you check my calculations? Are you happy with my calculations, or you see a flaw somewhere there? So what I did, I took a point on the parabola and I calculated, so it is, if x coordinate is x, the y coordinate is x squared for sure, and then I find the distance, the difference between x coordinates squared. Unfortunately, the difference between y coordinates squared gave me x to the power of 4, which was the main source of problem here, yes. So then if this one is x to the power of 4, and then x squared 2 times the first one times the second one is squared. And then I have this. I take the derivative by the chain rule, so I did this, which is correct. And then what I have done, I differentiate this one, which is also correct. Yes? Okay, so at the end, I should be able to solve that problem. So if I cannot, then probably, I don't know how they have done it. I haven't checked the book, but do you have any ideas how to solve this? Because the way that I see it, they are not very careful about solving this. So that's good, by the way, because if that's a practical problem, I have to live with it. Because usually in mathematics we are used to getting exact values, yes, but this doesn't happen usually in science and engineering or physical sciences and everything. So if you really need to solve this one at this level, you should be able to do something for it. Okay? We haven't talked about this in Math 4, that would be another part of a lesson, but I don't think even I can factorize it myself. Because if you want to solve a third degree, of course there is a method that you can find a solution for this third degree polynomial, but that is a very cumbersome formula, even I don't have it in my memory. So I would forego about it, and then I will see that if I can find any other way. So let us, by the way, use some tools to solve this, because in the body of the text they actually use softwares to solve the problems at the end. But that's also good, because the software on its own cannot come up to this idea to solve this problem. This is you, that you are making a problem to some point, and then you know how to use the software to solve that problem. First of all, if you don't mind, let us see how it works in tell me, how do you do it with GeoGebra or any software? Do you have any suggestions? Of course, might be there is a solve feature in GeoGebra as well, but I don't know. Let us check that. Solve. Yes. Okay, if you want to solve, it is usually better go to CAS view. But before going to CAS view, do you have any other suggestions? So you want to solve a polynomial equation. So one possible way is to draw the graph of that polynomial function and look for the intersection point of that graph with don't say that you don't know this, yes? You want to find the zeros of a polynomial. You draw the polynomial, the graph of the polynomial, and look where. Can you tell me where? This is extremely x-axis, the intersection points of the graph with the x-axis. So can you help me to so what was that? 2x to the power of what? 3 plus x minus 4 plus x minus 4. So that's the graph. And then I'm happy. So I would not be able to guess this number. So probably that number, first of all, you see that this is the graph of that function, and how many intersection points apparently you see is that one, yes? Of course, you should be, by the way, be careful. Here, is it guaranteed that there are no other solutions? Might be if I zoom out so much, I will probably find another route very much to the left or very much to the right. This is, by the way, be careful. Even if you have software in your hand, it doesn't mean that the software can solve your problem. Yes? Software is showing me probably the important point, but assume that I have another solution, I don't know, very, very much to the left. It's not clear here, but that's also a solution. Okay, but if you want to use, for example, GeoGebra, most of the time we have used that, hopefully we can do it. We go to intersection point, and or might be there is another feature in GeoGebra. Do you know about it? I think it will work. Let me first of all do this. Let us see if it works or not. Yes. And then you see that this number is 1.128 approximately. Yes. And of course you can increase the precision if you want. And that is clear because usually you can only solve polynomial equations with integer roots. And I already checked that there are no integers to be the solutions of this problem. Okay. So this means that this is the point, let us keep, I don't know, 1 decimal point. So remember, it's 1.1, yes? That's the point. But if I want to solve it, probably there is also another one. I think there was another feature here as well. Where is this? I don't see it right now. Might be here. Yes, the roots actually. So there is also this feature of roots, yes, for GeoGebra. Might be this is better. Why is this better? Because of the same reason that I told you. Might be there are some roots that I cannot see them right now. Yes, here I decided this is the only root, and then I asked GeoGebra to find the intersection point exactly what I see. But I think this feature might be better in this problem. So again, you just click on this one and you see the roots. That shows that there is one single root. Yes? Which the other one wasn't able to show that. Yes? So be careful. It's better to use the roots rather than just going and finding the point. Okay. So we take this number with us to the problem. So it's 1.1 approximately. And by the way, I also need a square of this number. So let me write x coordinate of point B, yes, and then squared, yes, to the power of 2. So that is the number, 1.27, okay. And the other one was 12.8. Was it? Is it right? 1 point, yes, probably approximately, that's correct. So 1.1 and 1.2 are the numbers that I'm looking for, okay. Okay, so let me just keep this one. And then I want to ask you something. Think about it, how I could confirm that there is only one solution without GeoGebra. That's also good you answer me. Okay, can you answer that question? If GeoGebra was not available, at least I was able to understand that there is exactly one root for this equation. When I say exactly one root, I mean real numbers, not complex numbers. Okay, how can I confirm without having GeoGebra available that there is exactly one root for this equation? And could I predict that the root should be positive, not negative? Can you predict that? Why the root is not negative? First of all, intuitively you know, I will come to you. First of all, what is the meaning of x being negative? X being negative is somewhere here, so it means that the distance is longer probably. I can find a shorter distance. This is intuitively, that's x shouldn't be negative. But forget about this. Just look at this equation. Why, if there is a solution, we don't know yet, but why, if there is a solution, this solution should be positive, not negative? Very, very simple question, yes?
Since we have -4, then if x was also negative, then...
Yes, because if x is negative, this term, because of cubic power, is negative, negative, negative. So 3 negative numbers cannot be equal to 0. So this means that the number here, if there exists, that is one, that's positive. Okay, the roots are positive. But can you confirm that there is exactly one root? Why there is exactly one root for this? This is something you could see even without having GeoGebra available. Why there is exactly one root for this equation? So these questions, everything that you need, you know, I am sure. But you need to think how you have to think about them. Yes?
When x in an equation is squared or an even power,
Yes.
then there is a possibility that x could be negative
Yes.
when we get our root.
Yes.
So then we have to answer that it's either positive or negative. But because it's cube or to the power of 3,
Yes.
then we can't assume. Then we
No,
can't.
my
assume.
question is that how do you know that there? So let us. My question is this: I want you to prove for me mathematically that there is only one positive root for this equation Even if you ask me what that number is, I was not able to answer it. I used GeoGebra to answer it for me. Yes? It doesn't mean GeoGebra knows better than me or better than mathematicians. GeoGebra is using the algorithm provided by mathematicians for them to get closer and closer to the root that you need. Okay, so that's probably, I don't know, I think might be GeoGebra is using an algorithm called Newton-Raphson's algorithm to get to that point. Okay? That's also part of mathematics, which is already implemented here in this problem. But my point is that, tell me, why do you expect that there is one single positive root for this equation? Based on just very, very simple calculations, following some logic in the back of your head. My guide for you is that it is somehow related to the derivative again. Yes?
If we take the derivatives 2 times.
Okay.
Yeah.
Then what happens?
We can calculate the terrace point.
Okay. Assume that you have the terrace point, then what? If you remember the picture from GeoGebra, yes, you are right, there was a terrace point. Okay, assume that you have the terrace point. How it will help you to confirm that there is exactly one positive root for this equation?
Then we can try with 2 different values.
No. Yes?
If x would be negative, then the first term would be negative, and the second term would be negative. That would not give an answer to the equation.
That is what actually Elias mentioned. So this means that the answer, if there exists, it's positive. But now, how can you confirm that actually this equation has a root and one root only? Because if you have a 3rd degree polynomial, it might happen that you have 3 roots, up to 3 roots, yes? That's the fundamental theorem of algebra. Okay, but let us take the derivative of this one. Okay, let me take the derivative of this one. What do you see? If I consider another function f of x equals to, it's completely unrelated, so I'm just making function again. I'm just looking at this function. And I take the derivative. It becomes 6x squared plus 1. Okay. How do you think, using the derivative, I can immediately confirm that at most one root is there? At most. I cannot confirm that there exists one root yet, but I am telling you, by looking at the derivative of this function, I can immediately tell you that there exists at most one real root for this equation, not more than that. Why? Why derivative helps me to do that? Yes?
Because the slope of the equation you get from the derivative, and if you find that the slope is always positive. Or zero.
Okay, better than that. There is a word for it. Why do you use a slope? If the derivative is positive, the function is? Yeah, you're right. That's exactly the geometrical way, but the function is increasing. Yes? So this means that this derivative, 6x squared plus 1, does not depend on the value of x. It is always positive. So it means that the function that I draw is always increasing. There is no way for the function to return back. Yes? So, I mean, if the function starts from here and goes up, in this situation there are no intersection points. But if I have this situation, I have to have one intersection point, not more. Because if I want to have another intersection point, at some point my graph should return back. When it returns back, it means that that part becomes decreasing. But this is not possible. Why? Because the function is always increasing. But this doesn't guarantee that I have one root. Because these two scenarios, one of them doesn't have any root. The function is always increasing. This function has one root, the function is increasing. How can I differentiate between these situations without drawing the graph? So is the question clear? So the function is increasing all the time. So this guarantees you that there is at most one root for my equation. Yes? But it doesn't guarantee you that there is necessarily a root. You have to somehow convince yourself why this is the case. You haven't studied this part formally, but intuitively everyone knows about it. So I mean that I can refer the exact name for the theorem that I am going to use, but even with that theorem is so simple to understand it intuitively that you don't need any proof for that. So how can I confirm that there is one intersection point at least? And this is related to the continuity of polynomial functions. So these are extremely important situations that you need to understand. So is this function continuous or not? Everyone hopefully knows that this is a polynomial function, and a polynomial function is always continuous. So it means that the graph of a polynomial function, I can draw it with one pen stroke. Okay? From the beginning to the end, in principle. Okay, but now let us assume that f of 0, let me just randomly for the time being calculate f of 0. For example, what is f of 0? Is minus 4. And let me calculate f of 2, for example. Okay, what happens? It becomes 8, 16, 8, 18 minus 4 is 14, yes? So what does it mean? It means that I don't need the details of the graph. I know that f of 0 is minus 4, so here is minus 4. So the graph should pass through this point. And at point 2, for example, it is where it is 14. So it means that at some point my graph is here. At a later time the graph should be here. And the graph is continuous. So what happens? You cannot jump from the x-axis. You have to go continuously from here to here. So it is inevitable. You have to do the intersection. So you cannot avoid intersecting the x-axis. Because at some point you were lower than the x-axis. At some point you are supposed to be higher than the x-axis. And you want to go from the lower point to the higher point continuously. So it means that you should have at least one intersection point. So you should have at least one intersection point. On the other hand, you have at most one intersection point. So this tells you that you have exactly one intersection point. Yes? Is that understandable? So the derivative helped me to understand that there is at most one root. And then this theorem, which is the name of this, is called intermediate value theorem. It's a big name for something that you can immediately understand, but of course the proof is different. Intermediate value theorem tells you that if you have a continuous function and you are below x-axis at some point and positive at the other point, so you have to cut the x-axis. That's more or less the same thing. So you see, you could understand a lot about this problem, but if you really want to find the value for it, okay, either you should do the algorithm developed by mathematicians by hand, or you should use the software. But I want you to understand the limitation of the software. Software was useless, even if you have the best software available. It was completely useless to solve this problem, unless you really know what are you doing. Yes? Okay, so now I think we can also check the back of the to see the solutions. So what I got, if I remember correctly, do you remember what was x? So finally p approximately is equal to what? 1.1 and 1.2, if I remember correctly, something like that. Yes? Okay, and then of course if you want to find the shortest distance, what you are supposed to do, you have to take this point, the x-coordinate, and put it here. Or here, better, yes. If you put that number here and calculate this, that gives you the distance. But by the way, did I confirm that this is the shortest distance? Intuitively it is clear, yes? Of course the terrace point is still a problem. This function might have a terrace point. But it is clear that this function doesn't have a maximum. Do you agree? Because if I am supposed to make this distance as large as possible, so I can go, for example, on this branch and go to infinity. So I am making the distance larger and larger. So intuitively, there is no maximum value for this function. So what you get is either the minimum or a terrace point. Yes? But how you can confirm that this is the minimum or maximum? You can immediately confirm it by the graphing that you had. Yes? So that was the graph of this function. The denominator of this function is always positive. Yes? Because that's the square root of something that's always positive. So the sign of the derivative depends on the sign of this. And you realize that the graph of this is at 1, and I don't remember exactly, I don't know, the trace points are somewhere here, and then you have this. Okay? So this means that if you are after this point, the function, the derivative is positive, because this is on the positive part. And before this point, this is lower than the x-axis, so it is negative. So it means that this point, on the left-hand side where the function is negative, it means that your value is decreasing. The function is decreasing, and then after that, the function is increasing. So this point that you found is exactly the the minimal point. It was not a terrace point. Is that understandable? Okay, so that was one problem. Actually, you see, you can learn a lot of things. So this is also good for learning mathematics. These strategies are for just solving one single problem. But I would say that if you want to be a good problem solver, try to design new questions out of the problem yourself. For example, of course, when you solve this with GeoGebra, don't be happy. Ask yourself, could I predict many properties of these things or not? Okay? Any questions here? Okay. So let me pause. By the way, let me check if the answer we got is somehow, hopefully the answer that is provided here, 5003. Yes, so that's the answer. Actually, they have written up to 3 decimal points exactly using GeoGebra 1.128. So if you remember, the answer was exactly that answer. So that's good. So you realize that where you can use software, but it is important to be able to solve the problem yourself. So let me just pick another one. We were talking about differential equations. Let us solve together. Let us solve 5001. Any questions here? Is that understandable for everyone? Where is the pen? Okay. 5001. Let me see if I can translate it. Okay, otherwise it might help me. So determine the constant a greater than 0. So a greater than 0 is guaranteed, but you are supposed to find it such that the function f of x equals to a to the power of 2x solves the following, the differential equation y prime minus y equals to 0 for all x. Okay, I can also ask you in this way. Instead of saying for all x, I would say that find a so that this is a solution for this. When I say a solution for this, it means automatically for all x's. I think this is a more straightforward question, yes? Okay, let us just a little bit talk about this again. So you should have what? You should understand the problem, okay? Let us stay at this point. How can I understand? Is the problem clear for you? Because you know that the way that I think for myself, this is a differential equation. This is not the case that any random function that I choose is a solution. So I want to fine-tune this constant in a way, if the problem is correct, so that this becomes a solution. This is at the level of my understanding, for the process of understanding for me. Okay? And then I need to have a plan. Okay, I want to hear from you now what the plan is. What the plan is. From my perspective, the plan should come to your mind in a matter of seconds. Because what do you say? I'm saying that this is supposed to be a solution to this differential equation. The first thing my brain goes for it is that what is the meaning of being a solution? And I think at this level, every one of you should actually realize this in a matter of seconds, yes, not minutes. So what is the meaning of this one to be a solution of that one? That's still at the level of my understanding about the problem. So what is the meaning of f of x be a solution to this, everyone? What is the meaning of that? What? Don't disappoint me, say something. What's the meaning of f of x being a solution of a differential equation? Come on. Yes, Kevin? Say it.
Then I'm having a hard time choosing the words.
No, it's very straightforward English. Your English is much better than these sentences. Okay, what's the meaning? Just tell me. When you say a function is a solution to a differential equation, what does it mean? Yes, Ruben?
If you put the function in the equation, it satisfies.
Yeah, that's it. So why do you hesitate to say that? Okay. So that's the plan. So now Ruben has a plan for the problem based on the definition of what a solution is. Yes, and I don't know. Everything seems very natural to think about it. Okay. So what I do now, I will try to do this here. So that is my plan. But there are many technical things that might come in. But be careful. I really think that having a plan is the hard part. And then try to see. So you have to see, go back and forth. Sometimes you have to do a lot of trial and error because you might know that the plan will work, is possible to work. Might be it's a good idea to start with the plan, but when I start doing the plan, I want to accomplish the plan, I have some technical problems that I cannot solve. Then you have to be ready to live it, to let it go and come back to another plan. But these problems are not that hard. Okay, so what you say is that I have to put this here and put it equal to 0. The technical problem is that I need to find the derivative of my function. So if I know the derivative of this kind of function in my head, that's okay. Otherwise, I know where to look for it, okay? So I would say that y is equal a to power 2x. What I need to do is to take the derivative of this function. I don't know how many of you remember this by heart. So if I write this, do you agree with that or not? No, because this is not a polynomial. It's an exponential function, yes? So the rule was different. So what is the rule? Do you remember, any of you? It was the same function, so the function repeats itself, but you have what? The natural logarithm of the base. But because of the chain rule, you have to multiply by the derivative of the exponent. So you see, I think you can manage it. Assume that you have the formula sheet in front of you. You know the derivative of this function, so hopefully you can do that yourself. And then you multiply this, so this becomes 2. So if you don't mind, let me write it as 2, and then ln of a is also a constant, so let me write it in one pair of brackets, and then I have a to the power of 2x. So at least I have a plan. My plan is to put this into that equation, and I solve one main technical problem here to take the derivative, which was not hard, and then the problem is that put it back there, okay? So instead of y prime, I put this expression, so this becomes 2 ln of a, and then I multiply it by a to power 2x, which is the y prime part, is minus y which is a to the power of 2x equals to 0. Yes? And I'm looking for a. So now that there is another technical problem in front of me, based on the experience that I got so far, I should be able to solve that problem. So, it's an equation that I am looking for a. Don't miss the goal. So that's the goal, to find a. But of course, I also have something else, x, involved in the problem. Okay, so how can I solve the problem now? Can you tell? This is a technical problem. There is no way. These technical problems, there are no ways that I can teach you. You should solve a lot of problems to be very fast in calculating these kinds of things. So you have a very good plan. You were able to do this part, but then you have to be creative in finding the correct technique to solve the problem. So how can I solve the problem? Do you have any suggestions for me? Yes?
So we can move over the a to the power of 2x.
Yes, so 2 ln of a, then multiplied by a to the power 2x equals to a to the power 2x, then what?
Then we divide.
Divide. So when you divide, you have to think about one technical problem, yes? What that is?
If it's equal to 0.
0. But it is not equal to 0, because a to any power cannot be equal to 0. So I am on the safe side, but think about these things. Sometimes they make problems for you. So you divide by a to the power of 2x. So then what you get is 2 ln of a. What is left on the other side is just 1. And then you are having one equation in one unknown. There is another technical problem. So you need to remember what the natural logarithm was in the first place, and then how to solve it. But hopefully you know what to do. What's a? So instead of that, the next part is to divide by 2. It's 0.5. Yes? And then what is a? These are standard Math 3C problems. The first time we'll learn this in Math 3C. So what, yes?
I don't know the exact number, but e to the power of 0.
No, that's the exact number, thank you. E to the power of 0.5. A is e to the power of 0.5. Yes? But e to the power of 0.5 can be simply written as the square root of e. Yes? That's correct. So the answer to this problem is exact here, and that's square root of e. Of course, if you want to see what that is, you have to use your calculator or whatever to calculate it. So that was a simple problem, yes? But you need to evaluate how many of you could solve it, I don't know, in 5 minutes. So this is important, by the way, okay? Let me see if there is another problem. Okay, that's also a good problem, I think. If 5005, I only look for the problems that I can translate, okay? Okay, 5005. For which values of the constant a the polynomial p of x defined as 2a x to the power of 3 plus 3x squared plus 6x plus 1. You want to find the values or value for a so that this polynomial is strictly increasing on the whole set of real numbers. Okay? P of x is strictly increasing on the whole R. So you want to find suitable value or values for a so that this given polynomial is strictly increasing on the whole R, not just one part increasing, the other part decreasing. But by the way, this last sentence is part of understanding the problem. Yes? Okay. How do you think about the problem? Again, you need to understand which parts of your math knowledge is relevant to this problem. If I ask you name one concept that definitely is relevant to this problem, which concept do you name it? Yes?
Derivative.
The derivative. Why? Because we just also reviewed today. If the derivative is always positive, so it means that what happens? It means that the function is always increasing. But that problem was different. This is now stated in a different way. So you want to fine-tune this parameter a so that this given polynomial is strictly increasing always. Instead of saying always increasing, they have used this phrase. It's strictly increasing on the whole R. It means always. Yes? Okay, so the first thing, I hope that you agree. You have a plan now. So your plan is to differentiate the function and see that how can I force the derivative to be positive all the time. Is that clear? Because you want to have this increasing all the time, it means that its derivative should be positive all the time. So what does it mean? It means that the first step that I want to do is to differentiate the function, which is extremely simple. It's 6ax squared plus 6x plus 6. Can I divide by 6 here? Please tell me, 2 seconds. Can I divide by 6 now? Yes or no? I mean, can I just divide by 6 and write ax squared plus x plus 6 plus 1? Yes or no? 2 seconds. Yes or no? I mean, can I just throw 6 away and say px prime is ax squared plus x plus 1? Yes or no? Yes or no?
For the purposes of increasing, yes. Because it's always increasing. Or it
No,
has the
what
same
I'm saying,
behavior.
I got this derivative, and then on the paper I write this. Is that correct or wrong? Yeah, it is wrong. Yes? If p prime of x is this guy, p prime of x cannot be this guy. Unless you divide this by 6, then that is logical. Yes? So if you have an expression, you cannot just rescale this expression whatever you want to. But if you have inequalities, equations, and things like that, you can divide both sides by that number. Yes? If you want to get rid of 6, there is one way in this case, to divide this by 6 as well. But what Kevin also mentioned is correct. The point, so it means that you need to differentiate between these logics. So it means that now I put the derivative equal to, if I put the derivative to, I want to force the derivative to be positive all the time. So then it means that, look, instead of the derivative, I put this expression greater than 0. But now can I get rid of 6 here? Yes. Because I divide everything by 6, not only on the left-hand side, but also on the right-hand side. What is the logic? The logic is that if this number is supposed to be larger than 0, this number divided by 6 is still larger than 0. There is a logic behind that, okay? So this means that ax squared plus x plus 1 is larger than 0. Okay? Okay, so now I understand what is the problem. The problem is to force this to be always true. Be careful, that's important, on the whole R. So it means that I want to have this be greater than 0 independent of the choice that I make for x. Because I want to have this correct on the whole real numbers. Then again you have to think, okay, how can I choose which values of a, if I choose them, this will give me this inequality to be true all the time for every x that I choose. That's another technical problem that you have to solve right now. Can you tell me, how do you think about the problem? By the way, because I don't understand what you're talking about, the point is that every problem should have a plan again. So what is your plan? So that is another problem, because you see, it's not a technical problem, by the way. I use that part of my knowledge about the derivative, reduce this problem to a more concrete problem. Yes? It was not that very concrete here, but that's more or less concrete because that's an inequality. So I reduce the problem to a more concrete problem that I can think, hopefully, more efficient on it. Yes? But then still, it doesn't mean that, okay, I have to do things randomly again in the middle. You should have another plan, because now your problem has changed. The problem is no longer the original problem. The problem is completely new. It means that if you, by the way, this is one skill that you have to learn, is that when you have this problem, you can just completely try to ignore what you had before and then try to focus only on this problem. But this is a new problem, so if that's a new problem, you need a new strategy. Okay? So you have to have a plan for it, otherwise it would be random guess again. So what's your plan? You want to have this quadratic polynomial to be larger than 0 all the time. What part of mathematics will help you that you have already studied? Can you give me one word for it? If one part of mathematics that you have studied so far is relevant to this later problem, what that part is? So you see, I just want you to give me a word, because this more or less should be clear where to go and look for. If you don't have that idea in your head, you have a lot of math knowledge in front of you. You really don't know right now where to look for it. So you should narrow it down. So at least, can you tell me, I don't know, a keyword for this problem? So this is not hard, by the way, to find. So try to find the definitions. So if you want to ask yourself, what is this guy here? Can you give me a name for this guy? A generic name for this guy. What's that? A second degree polynomial. Yes? Okay. So I have a second degree polynomial larger than 0. Okay. But one possibility that you have learned so far is find a relation between algebra and geometry. This is really, really helpful in solving problems. So if I want to solve a problem, algebraically it seems hard, we don't have any clue what to do, we can translate the problem into a geometrical language. When I say geometrical language, it means a graph of the function. Yes? Okay, so this means that you need to remember that part of knowledge about the parabolas, because the graph of quadratic equations are called parabolas. Yes? So then you see that you have to start learning how to narrow these things down. Okay, so parabolas. So for the momentarily, you go to a scratch paper and try to review what you have learned about a graph of parabolas. But then you immediately realize something. Is this number important for drawing my parabola? Yes, if you have a little bit of knowledge, remember, this means that if this is positive, it opens up, and if this is negative, it opens down. Yes? But let us consider, I don't know, this is the way, by the way, I solve the problem, because I don't know the solution yet. Okay? So what I do, I would say that let us consider A positive. First of all, what about A 0? Can A be equal to 0? Why not? Because they have asked me to choose A, some number. But my question is that A equals to 0 is an option or not? Why not? Yes?
Because if x is a big negative number.
Yes, exactly. This means that your understanding is completely correct. Because some people, so this means that's a very, very good success to understand this. Because if a puts 0, some people solve this inequality. The problem is not solving the inequality, the problem is different. If a is 0, I face a polynomial which is not always positive. It is positive for values greater than -1. So it means that if I choose, for example, x to be -5, then it becomes negative. So it is clear that I have to rule out the value 0 for a. So I don't have any problems. So now I am relieved because I have to consider two cases. A equals to 0 is excluded from my solution. So if a is positive, I have this situation. If a is negative, I have this situation. Okay, but because I want to see where this expression is positive, it means that I have to understand the relative location of my parabola with the x-axis. Yes? Because if the parabola is always above the x-axis, it means it is always positive. And if it is always below the x-axis, it means that's always negative. Okay? So in this case, I have three scenarios, yes? I might have this scenario. I might have this scenario. I might have this scenario. Yes? If a is positive, it means that my parabola opens up. This means that I have three general categories here. But for the purpose of the problem, which is needed in this case? Which one I want to have? This one or that one or that one? Which one of them is suitable for the purpose of the problem? It's simple, just tell it to me, yes? Yes? The first one. Why the second one is not good? Because the second one has one touch with the x-axis. It means that my parabola becomes 0 at one point. I don't want it. I want to be strictly positive. So why this is not working? For the same reason, I have 2 points where it is 0, and I have a bunch of points where the parabola is below the x-axis. So this means that I have to rule this out, I have to rule this out. So this is one possibility, if a is positive. Let us immediately concentrate on a negative as well. So this is the scratch work, by the way, I do myself, but probably a little bit in shorter time, yes? So what happens? I might have this scenario, I might have this scenario, I might have this scenario. Which one is acceptable here? Is there any one of them? Yes? None. Because this one is always negative. I don't want it. This is not always negative, but it is only 0. It is always 0 or negative. I don't want it. And what happens here? Some part of it is above the x-axis, which I want, but this is not always. So it means that this part is not acceptable. So it means that I am now relieved. Yes, I just throw this away. I only need to concentrate on positive a's. Is that understandable? Yes or no? Okay. But is this the whole story? It's not finished yet. I realize that a cannot be negative. A should be positive. But my question for you, is it the case that all positive values for a are acceptable? No. Yes? Because now you realize you want to force your parabola to be of this form, not this form and this form. A positive gives you three possibilities, but you want to narrow this situation down into one single case where you have this one. Okay? This is the help that you get from geometry, but geometry is not good for calculating exact values. Algebra is. So now you have to go back to algebra. Okay, can you tell me, what should I implement on this so that I get this desired situation? How do you really force the parabola not to be like this, not to be like this, to be like this? How do you force your parabola to be this? Yes?
If you solve the equation in a way which only gives one answer, meaning that it will be the one with which only intersects one, then all a's larger than that will always be over the...
No, you are making problem complicated. The method that you are saying is true, but you are making it unnecessarily complicated. You want to have this situation, come on, this is easy. This means that your parabola has one single root. Yes? This means that you have two intersection points, so two roots. But this means that you shouldn't have any roots for your parabola. What does it mean? It means that if I put this equal to 0, I demand that there are no roots for this. Because if this equation doesn't have any roots, it means that my parabola will not intersect the x-axis. And because I have already considered a to be positive, I will get this scenario. Okay, when this doesn't have any roots, that is very simple. So the delta should be negative. Yes? So because if you solve this problem, how do you solve this? You get x is equal to minus 1 plus or minus the square root of b squared, which is 1 minus 4a. And then divided by 2a. Yes? Is that right? This is what you get to solve. But you want to do it something that this is negative, because if 1 minus 4a is negative, it means that minus 4a is less than minus 1. This I divide by minus 4. Remember, you have to swap the sign. It becomes 1 over 4. Yes? So if a is larger than 1 over 4, under the square root becomes negative, and there are no roots for this. And if there are no roots, it means that I am facing this situation. Because when a is greater than 1 over 4, automatically it is also positive. Yes? So that's the answer. So a should be larger than 1 over 4. I don't know. Is that understandable or... So let me check the answer. 5005. Yes. They have written a greater than or equal to 1 over 4. I think, yeah, that is correct. Because if a is equal to 1 over 4, what will happen? If a is equal to 1 over 4, the point is that the starting point was that this should be greater than or equal to 0. So this will also be greater than or equal to 0. This should be also greater than or equal to 0. So it means that having 0 is also acceptable. Okay, so that scenario is also acceptable. Because if the derivative is 0 at some single points, that doesn't hurt the strictly increasing part. Yes, but this should be... So by the way, another way you understand that is that if you put 1 over 4 there, this becomes 1 over 4x squared plus x plus 1, which is, by the way, equals to... Let me see. It becomes 1 over 2x plus 1 squared, which is always non-negative. Because this is a squaring pattern. This becomes this number. And this is non-negative always. It becomes 0 if x is equal to minus 2. Okay? Yes, that's correct. It should be greater than or equal to 1 over 4. Because the reason is that even if they talk about strictly increasing, you should start with this equation. Because, but this is technical. If the derivative is 0 at some isolated points or some finite number of points, it will not hurt the strictly increasing one. For example, you see the function f of x equals to x to the power of 3. If you draw the graph of this function, this is a function like this. If I ask you, is this function strictly increasing all the time, the answer is yes. But if you take the derivative is 3x squared. But if I ask you, is the derivative always positive, you should say no. It's always positive with one exception, and that exception is that if x is 0. So the derivative is always positive, but it is 0 at one single point, and that is where I choose x equals to 0. But you see, still, even though this is greater than or equal to 0, the function is strictly increasing, not just increasing. So that's my bad, and I have to start. I didn't know that they will talk about this, but anyway. So you have to consider that one, so this means that this should be greater than or equal to 0. Yes? That's the correct one. Okay. I think it's good to stop here. Might be we use one more session on these problems, but I think there are very nice topics that I see is coming up that I will try to cover as many as I can. Actually, I don't know what was the purpose of this, but I don't think they are included in the standard Math 5 lesson, but they are very nice topics. We can continue with them. Any questions? Yeah, thank you.